Composition of functions. We're going to start with a review of functions and how the notation works, because it's often the case that this is what causes students to stumble. F of x is equal to 2x plus 7, and we say all the time that the x is a variable. And you're used to seeing a couple cases here. You're used to seeing what happens whenever we plug in variables such as x, and we plug in values such as 3, right? So f of 3 would be 2 times 3 plus 7. This is why we get frustrated when students write things like f of x is equal to 2 times 3 plus 7. No, we want the inputs to match. So we can evaluate f for values such as 4. F of 4 equals 2 times 4 plus 7. We can evaluate it for variables. F of a is equal to 2 times a plus 7. We can evaluate it for things like lightning bolt. F of lightning bolt is 2 times lightning bolt plus 7. The lightning bolt is a silly example, but it gets the point across. That is that f, the function f, is the set of instructions: take the input, double it, then add 7. So you can think of this two ways. You can say, well, x has only ever been a placeholder. We're waiting to sign something on the dotted line. We'll be representing this with a dotted box. If you put an x in there, you get f of x equals 2x plus 7. You put a 3 in there, you'll get f of 3 equals 2 times 3 plus 7. So composition of functions is a new idea that says what we want to do is we're going to take an input and we're going to do operation G, then we're going to do operation F. It is not multiplication. So let's say we're given f of x is equal to 2x plus 7, and we want to do the functional composition f composed of g of x. So the input is going to be x. What this looks like is take a g of x and place it into f. F, remember, takes that input and does the following set of instructions: double it and add 7. Well, what is being placed on the dotted line there? G of x. So what we're going to place on the dotted line, in my case the dotted box here, is g of x. So let's give ourselves a function to work with here. Let's say g of x was x squared. In other words, g says take whatever I give you and square it. Well, now I can replace my g of x's in the boxes with x squared. So at the end of all my work, f of g of x is 2x squared plus 7. This makes some sense. Remember I said we're going to do g, then f. So if you give me an x, I'm going to first square it, then I will double it and add 7. Let's try one more example. Let's say I wanted to do g composed of f. Note that this will run the other way. Take f of x and plug it into g. G takes something, it takes that input and squares it. What's signed on the dotted line this time? F of x. F of x is the same thing as 2x squared plus 7. 2x plus 7 squared. Take that, multiply it out. You get 4x squared plus 28x plus 49. A couple of things to note right off the bat here. We get that f composed of g is not the same thing as g composed of f, so the order matters. It's totally valid to say g composed of g of x. It just says do g, then do g again. And finally, it can be helpful to see what actually happens when you plug a value in. And the blue box up there is all the stuff we've already found out. So say we want to evaluate it at 3, f composed of g at 3. We know that the function is 2x squared plus 7, so I just plug my 3 into there and I get 25. Alternatively, you could think of this as first do g. So take that number 3, the input, and do operation g, square it. We get the purple 9 right there. Then we do F to that latest output, that purple 9, and we get 25. So both ways we end up with a 25. Looking at it this way has one advantage, and that is the purple 9 is in the range of G. So we need to make sure, is that 9 in the domain of F? So the domains and range of compositional functions is a bit tricky. I suggest you look at it in this fashion where we're taking those outputs from G and using them as the new inputs for F.